100 billion stars can feel like an ending, a complete inventory, a ceiling so high that your brain stops climbing and just calls it infinite. For most of human history, that was the emotional job of the Milky Way, a pale river across the night that made you feel surrounded, centered, and strangely important. But modern astronomy has a brutal talent. It doesn't just add new sights, it changes the meaning of old ones. It takes the thing you thought was everything and places it inside something larger until your everything looks like a local neighborhood street on a planet you can't even locate on the map. The Milky Way is still enormous. Even the conservative, headline-friendly numbers are ridiculous on a human scale. Our galaxy's bright disk spans about 100,000 light-years. Light, the fastest thing the universe allows, needs 100,000 years just to cross the part of our home that shines most obviously. And inside that disk is a population of stars so large that astronomers can only speak in ranges, hundreds of billions. Not because anyone is being vague, but because counting stars in a dusty spiral while living inside, it is like trying to count every window in a city while standing in the middle of its busiest intersection. You see what's near you, you infer what's far, and you accept that the full answer is always one better instrument away. That living inside it detail matters. It's the trap the Milky Way sets for our intuition. When you look up, every naked eye star you can see belongs to this galaxy. It makes the Milky Way feel like a container, like the sky is the lid. For a long time, that was the best story we had. But location is not the same as scale, and being inside something huge can make you confuse it for the whole. Astronomers learned that the hard way. For centuries, they tried to map the Milky Way like explorers tracing coastlines, only to discover they were mapping a world with enormous continents erased. The galaxy is threaded with dust, cold grains mixed into giant clouds of gas, concentrated in the spiral arms and thickest along the plane of the disk. Visible light hits those clouds and gets scattered or swallowed. Whole regions vanish. If you build your understanding only from visible light, you are drawing air with a missing color, and you don't even realize how much of the picture that color was supposed to carry. Still, progress came. Radio astronomy could slip through dust that would stop optical light. Infrared could do the same, because longer wavelengths are less easily scattered by those grains. With enough patience, you can map the galaxy in pieces. Spiral arms traced by gas, a crowded center inferred through motion, a rotating disk measured by the Doppler shift of hydrogen lines. Over time, a consensus formed, a barred spiral, a dense central region, a disk and halo. An object so large it could hold your awe for a lifetime. Then a different kind of observation snapped the scale like a twig. It didn't start with a bigger mirror, it started with a dare. In the mid-1990s, astronomers did something that sounded, at the time, like a waste of one of the most valuable machines humanity had ever built. They pointed the Hubble Space Telescope at a patch of sky that looked empty. Not empty like a desert is empty. Empty like a black pixel on a screen. A place chosen precisely because no obvious stars or galaxies were getting in the way. And then they let Hubble stare. Not for minutes, not for a single orbit, for days. For roughly 10 days of accumulated exposure, letting faint light pile up on a detector like dust settling on a shelf. What came back wasn't empty. It was crowded. That one nothing patch contained on the order of 3,000 galaxies, each one a whole system of stars, gas and dark matter, each one a separate story, running on cosmic time. The image became famous because it did more than show galaxies. It showed a new fact about reality. Most of the universe is not where the bright things are. Most of the universe is in the places you would have ignored. That discovery should have been enough to permanently humble us. But Hubble had a limit baked into physics. It mostly sees invisible and near-visible wavelengths, and the farther you look, the more the universe refuses to cooperate with visible light, because the universe expands. Expansion doesn't just push galaxies away, it stretches the light traveling through space. Over billions of years, wavelengths get pulled longer and longer. Visible light shifts toward red, then beyond red, past the range your eyes can see, past the range where a visible light telescope is comfortable. The oldest galaxies, the earliest stars, the first major structures, their light has been stretched by the universe itself into infrared. If you want the earliest chapters, you need an instrument that lives in infrared the way your eyes live in daylight. That is where James Webb enters the story, and why it feels, in practice, like the universe suddenly turned the brightness knob up. Webb was built to be cold. Not cold as a convenience. Cold as an absolute requirement. Infrared detectors don't just capture cosmic heat, they are vulnerable to it. If the telescope is warm, the telescope glows in infrared and blinds itself. The faint signals you care about drown under the instrument's own thermal noise. So, Webb carries a sunshield the size of a tennis court and hides in permanent shadow, letting its cold side drop to around 40 kelvins. So cold that the telescope's own heat becomes quiet enough for the universe to speak. One of its instruments, tuned for mid-infrared, needs to be colder still, cooled by a cryocooler down to just a few kelvins so it can listen to even fainter whispers. Webb was also built to collect light like a trap. Its primary mirror spans 6.5 meters, assembled from 18 hexagonal segments coated in gold to reflect infrared efficiently. This isn't a cosmetic detail. It's how you turn a distant, ancient photon into a data point. The bigger the mirror, the more photons you catch. The more photons you catch, the less the universe can hide behind darkness. When Webb began returning deep-field images, it didn't simply repeat Hubble's stunt. It changed what the stunt meant. One of Webb's first public deep views centered on a galaxy cluster called SMACS 0723. If you glance at the result casually, you see what you expect. Countless galaxies scattered like embers. But look again, and you notice the strange bends and arcs, the stretched shapes, the smeared crescents of light. That isn't artistic blur. That is gravity. A massive cluster like SMACS 0723 warps space so strongly that it bends the paths of photons coming from galaxies far behind it. It acts like a lens, magnifying and distorting background galaxies that would otherwise be too faint to see. Webb's deep field image is not only a photograph of distant galaxies, it is a photograph of mass itself at work. Visible matter and invisible matter together shaping the view. And because Webb sees in infrared, it captures galaxies whose light has been traveling since the universe was young, their signals stretched into the band Webb was designed to catch. This is the moment the Milky Way shrinks. Because when you realize that a blank patch of sky can contain thousands of galaxies, the number of stars in your own stops feeling like a grand total and starts feeling like one entry in an absurd catalogue. Our galaxy, with its hundreds of billions, is not special for being large. It's just one large spiral among many large spirals. The Milky Way is a barred spiral with a central bar of densely packed stars and arms winding outward, a structure shaped by gravity over billions of years. From the inside, it's breathtaking. From the outside, it's a type. And it gets worse, because Webb doesn't just show the universe is crowded, it shows the universe was crowded early. When you look far enough, you are looking back in time. That isn't poetry, it's the speed of light. A photon from a galaxy a billion light years away has been traveling for a billion years. You see it as it was, not as it is. So, when Webb shows you galaxies at enormous distances, it is showing you galaxies at enormous look-back times, snapshots from an era when the universe was a fraction of its current age. That has consequences. Before Webb, cosmology already had a successful story about how structure forms. After the Big Bang, the universe expanded and cooled. Tiny density fluctuations, slight overdensities, grew under gravity. Dark matter, which doesn't interact with light, began clumping first, forming invisible scaffolding. Gas fell into those wells. Stars ignited. Small proto-galaxies formed. Then they merged, slowly building larger galaxies over hundreds of millions and then billions of years. This gradual build is one of the reasons the cosmic web exists, filaments and nodes emerging from the growth of those early fluctuations. The story is powerful because it matches so much evidence from the distribution of galaxies to the large-scale patterns imprinted in the oldest light we can detect. But a story that works is not a story that can't be surprised. Webb's deep fields pushed into the first few hundred million years after the Big Bang, the era when galaxies were expected to be small, chaotic, and just beginning their lives. Astronomers expected dim clumps. They expected irregular, fragile structures. They expected the universe to still look like it was assembling its first cities. And then Webb started showing systems that looked too built, not in the sense that they looked like modern galaxies with perfect spiral arms. Early galaxies are still messy, but some appeared brighter than expected, more massive than expected, more numerous at certain epochs than expected. In other words, they looked like the universe was constructing big things earlier than the simplest versions of our models predicted. That does not mean the Big Bang is wrong. The foundation of modern cosmology is still standing, but it does mean the first chapters of galaxy growth may have plot twists we didn't write into the early drafts. At this point, you have to be careful. Too massive can mean different things depending on how you infer mass. Early claims often begin with photometric estimates, colors measured across filters, then get refined by spectroscopy, lensing models, and better assumptions about how stellar populations behave. Dust can hide star formation. Emission lines can make galaxies look brighter in a filter than their stars alone would suggest. The universe is full of ways to trick you if you treat light like a simple reporter. But even after you acknowledge every caveat, one stubborn fact remains. Webb is showing a young universe filled with more structure, more activity, and more light than we once expected to directly observe. And that change lands in your gut when you return to the Milky Way, because our galaxy feels old. 10 billion years is older than almost anything a human mind can truly hold. Yet in cosmic terms, the Milky Way is not among the earliest giants. It formed into its recognizable self long after the first galaxies began seeding the universe with heavy elements, long after the first starbursts burned through primordial gas, long after the first black holes began feeding and throwing energy back into their surroundings. We are not at the beginning of the story. We are an event in the middle of it, happening on one branch of a web that was already taking shape. So when you hear the Milky Way has 100 billion stars, you should feel awe. But you should also feel the other thing Webb keeps forcing on us. Scale is not just size. Scale is context. And the moment you place the Milky Way inside the deep field reality, our galaxy stops being a grand container and becomes a local address, a spiral in a modest group, in a filament, in a supercluster, in a universe that doesn't just contain many galaxies, but hides most of them in the places we used to call empty. That is the emotional shift. But the scientific shift is sharper. Because once you accept that the sky is saturated with galaxies, and once you accept that Webb can see back into the era when galaxies were supposed to be small and newborn, you arrive at a question that is both technical and terrifying. To really feel why this is so disorienting, you have to remember how fragile our measurements used to be. There was a time when distance in astronomy was almost a philosophical concept. Stars looked like pinpoints. Without depth cues, the sky behaved like a painted dome. Early astronomers could argue about whether the Milky Way was a thin disk, a thick cloud, or a small swarm centered on the sun, and no one could end the argument with a tape measure. The first crack in that ignorance was parallax, the tiny apparent shift of a nearby star against more distant background stars as Earth moves from one side of its orbit to the other. It's the same trick your brain uses to judge depth when you close one eye and then the other. Parallax is brutally honest because it is geometry. But geometry has limits. The farther a star is, the smaller its parallax becomes, until the shift is so tiny that even your best instruments can't separate it from noise. So, astronomy climbed a ladder. For nearby stars, parallax. For farther distances, standard candles. Objects whose true brightness you can infer, so their observed brightness tells you how far they are. Cepheid variable stars became one of the most important rungs. They pulse in brightness with a period that correlates with their intrinsic luminosity. Measure the period, you get the true brightness. Compare true brightness to observed brightness, you get distance. It was a brilliant hack, turning a star's heartbeat into a ruler. But notice what that ladder depends on. Light that reaches you in the first place. Now, imagine building your entire map of your home city with a flashlight that can only shine through clear air, while half the streets are permanently covered in thick fog. You don't stop mapping, you infer, you model, you estimate what should be behind the fog based on what you can see at the edges. That is what the Milky Way did to us for generations. Dust didn't just hide distant galaxies behind the plane, it hid our own structure from us. It made our galaxy feel simpler than it is. It made some directions look emptier and others look more crowded. It made the center, where so much of the mass and action lives, into a silhouette you had to reconstruct through indirect clues. The Milky Way's disk is not a polite, evenly lit object. It's a crowded, messy system with star-forming regions, supernova remnants, giant molecular clouds, and a central bulge packed with old stars. The galaxy's central black hole, Sagittarius A star, sits at the heart of that chaos, and around it is a region so dense and dust-choked that visible light struggles to tell you anything, but something is there. This is why maps of the galaxy always came with disclaimers. This is why different surveys could disagree on the exact shape of arms, the number of major arms versus spurs, the thickness of the disk, the extent of outer structures. The Milky Way wasn't changing. Our window into it was. Infrared astronomy widened that window long before Webb. Space-based infrared telescopes like Spitzer helped reveal star formation inside dust clouds and trace structures that visible light surveys couldn't cleanly see. Spitzer's view of the Milky Way looked like someone lifted a veil. Glowing knots where stars were being born, filaments of warm dust, regions that had been invisible suddenly speaking in heat and longer wavelengths, but Spitzer had limits. Smaller mirror, lower sensitivity. It could show that the fog hid things, but not always resolve the deepest, faintest, most distant details hidden inside that fog. So when Webb arrives, it doesn't just reach outward to the early universe. It changes how the Milky Way fits into the same logic. Because Webb's superpower, infrared sensitivity plus extreme cold, doesn't care whether the dust is between you and a newborn star in your own spiral arm or between you and a galaxy that existed before your planet formed. Dust is dust. Long wavelengths punch through it either way. This is why the comparison becomes unavoidable. For a long time, we treated the Milky Way like a primary object and the rest of the universe like background scenery. Webb flips that emotional priority. It forces you to see your galaxy as a single example inside a much larger population. And then it forces you to see the population itself as older and more aggressive than your intuition wants to allow. The deep field idea is the purest version of that flip. The trick is simple: integrate light for a long time, so that the faintest sources accumulate enough signal to stand out from noise. But the consequences are not simple, because deep fields reveal a universe that is not mostly empty space with occasional islands, but mostly islands at every distance and scale you are able to resolve. Hubble's 10-day stare was the first punch. It made empty meaningless. But even Hubble's punch came with the soft gloves of visible light. The oldest, faintest galaxies are redshifted and dust-obscured, and many of them live in a regime where Hubble sees only hints. Webb removes the gloves. When Webb's first deep field dropped, people talked about it like a single picture. That's how it entered culture, a stunning image you could zoom into until it felt like falling. But the deeper truth is that it wasn't just a picture. It was a demonstration of capability, a proof that a new window was open, that you could combine a deep exposure with gravitational lensing and infrared sensitivity and suddenly retrieve galaxies that, a few years earlier, were below the practical threshold of direct imaging. Gravitational lensing is worth sitting with for a second, because it is one of those cosmic facts that feels like it shouldn't be allowed. Mass warps space-time. Space-time tells light how to move, so a galaxy cluster becomes an optical tool, even though it was never built for that purpose. It can magnify distant galaxies, stretch them into arcs, split them into multiple images, and brighten them enough for our instruments to study. In a sense, the universe provides its own magnifying glass. You just have to know where to place your telescope. Webb's deep field used that gift. SMACS0723 sits like a heavy knot of mass, and behind it are galaxies whose light has taken most of cosmic history to arrive. Some of that light left when the universe was still learning how to make stars efficiently. Some of it left before the Milky Way existed in anything like its modern form. And because the cluster lenses those background galaxies, you see them not as vague smudges, but as structures. Pieces, clumps, shapes, star-forming regions, hints of how these early systems were assembling themselves. This is where the grain of sand analogy lives. The deep field covers a tiny patch of sky compared to the full sphere around us. You can hide it behind something small held at arm's length, and yet it contains thousands of galaxies. The point isn't the object you hold up. The point is the math it implies. If a tiny patch contains thousands, the whole sky contains a number that doesn't fit comfortably inside the human mind. This is why galaxy counts keep inflating as instruments improve. You don't just see more distant galaxies. You see more faint galaxies. You discover populations that were always there but were below your detection limit. The universe didn't get busier. You got better at noticing. Now put that against the Milky Way. Inside our galaxy, dust and crowding make it difficult to see through the plane, difficult to observe the central region, difficult to measure faint outer structures. Outside our galaxy, distance and redshift and faintness make it difficult to see the earliest light. Webb attacks both problems with the same physics: infrared sensitivity and cold stability. It is not a coincidence that Webb's name became a shorthand for "the universe is bigger than you think." It isn't just seeing farther, it's changing what farther means, because farther in astronomy is always also older. This is the part that can mess with your sense of time. In everyday life, the past is behind you in memory. In cosmology, the past is overhead. It is literally laid across the sky in shells. Nearby galaxies are recent history. Distant galaxies are ancient history. The cosmic microwave background, the oldest light we can see, marks an epoch when the universe became transparent to radiation, leaving behind a faint glow that still fills the sky. Everything beyond that is not hidden by dust, not hidden by distance, but hidden by the fact that light could not travel freely before that time. So, Webb isn't just peering into darkness, it's walking backward along the universe's timeline until the timeline itself runs into a wall. And still, within the epochs Webb can access, it has been finding surprises. Part of why those surprises feel so dramatic is that the early universe is not just farther away. It is physically different. The universe was denser, galaxies were closer, gas was more abundant, star formation was more intense in many environments. Mergers were more common. The processes that build structure were running hotter. In a young universe, gravity has less time to work, but it also has more material to work with. And the whole arena is more tightly packed. Models capture a lot of this, but models are not the universe. They are controlled stories written in equations and assumptions, calibrated to what we used to be able to observe. When Webb shows you actual data from those epochs, it is like hearing the original recording after decades of listening to a cover version. Some of what Webb revealed was exactly what astronomers hoped for. Galaxies in chaotic youth, clumpy structures, intense star-forming regions, systems that look like they are still assembling. But alongside those, there were candidates that looked more developed than the simplest expectations, brighter than anticipated at a given time, more abundant in certain surveys, potentially more massive at earlier epochs. The careful way to say it is that Webb's data has pushed on the inferred rates and timelines of early star formation and early galaxy growth. The dramatic way to say it is that Webb seems to have caught the universe cheating, building big, fast, early, as if it didn't read the part of the script where it was supposed to take its time. If you're tempted to lean into that drama, good. This is where the story earns it. But the drama has to be disciplined, because the universe is also an expert at making you over-interpret a photograph. A distant galaxy can look massive because its light is amplified by lensing in a way you haven't fully modeled. It can look bright because strong emission lines fall into the filter you used, artificially boosting the measured brightness. It can look old because dust reddens its colors, making it resemble an older stellar population. It can look like a large, settled structure when, in reality, you are seeing multiple smaller components blended together. This is why astronomers treat early claims as candidates, then do the slow work. Spectroscopy, better lens models, deeper exposures, cross-checks. But even after you grant every trap, the universe keeps leaving a residue of tension that won't wash away. Too many interesting objects show up too early, across too many independent analyses, for the discomfort to be dismissed as a single measurement mistake. And once you feel that discomfort, you look back at the Milky Way and realize the insult is twofold. First, our galaxy is not a special island in a mostly empty ocean. It is one of an enormous number of islands in a sea so crowded that empty is just an artifact of weak eyesight. Second, our galaxy is not an early pioneer, it is a later chapter, forming in a cosmos that had already been building and rebuilding for billions of years. That is what makes Webb's images emotionally sharp. They aren't just beautiful, they are corrective. They take the story you tell yourself about being central, about being early, about being surrounded by a small, friendly neighborhood of stars. And they move your coordinates. They show you a map where your location is not the center of anything but your own immediate experience. So yes, the Milky Way has 100 billion stars. You should still let that number hit. You should still let it be enormous, but you should also let Webb's deep field do what it was always going to do. Put your galaxy into a crowd, then put that crowd into a history, and then make you confront the fact that the history seems to start building its biggest monuments much earlier than we expected. And there's a cruel trick hidden in how quickly your mind adapts. The first time you see a deep field, you feel the vertigo. The second time, you start looking for your favorite shapes. Spirals, ellipses, neat little pinwheels. By the third time, thousands of galaxies starts to sound like a statistic, not a shock. Don't let it become background. Every faint smudge is a structure held together by gravity. Every warm-colored dot is a swarm of suns. Every arc is a reminder that space can be bent, and that mass you can't see is doing most of the bending. Webb didn't manufacture any of this. It didn't paint galaxies onto darkness. It only collected photons that had been traveling, uninterrupted, through expanding space since long before there were humans to care. The universe was always this crowded. The only thing that changed was our ability to catch its light, hold it still, and finally read what it has been saying all along. And now that we can read it, the next pages are already contradicting what we expected, quietly. Because once you accept that Webb can see into the first few 100 million years, and once you accept that some of what it sees looks surprisingly mature, you arrive at a question that is both technical and terrifying. If the early universe was supposed to build slowly, why is Webb catching it already building giants? Because slow was always a simplification, and Webb is finally showing us the parts of the early universe where the simplification breaks. The standard picture of galaxy formation isn't a fairy tale about finished spirals materializing in darkness. It's a chain reaction. First, dark matter clumps, not because it's magical, but because it's quiet. Ordinary gas in the early universe is hot, pressurized, and collisional. It bangs into itself, heats itself, resists collapse. Dark matter doesn't do that. It can start collapsing into gravitational wells while normal matter is still fighting its own heat. Those wells become invisible scaffolding, halos, hundreds of thousands of light years across, with gravity strong enough to drag gas into them. Gas falls in, cools, fragments, and ignites into stars. Stars explode, metals appear. Cooling becomes easier. Star formation accelerates. Small systems merge into bigger systems, over and over. That's the logic behind hierarchical growth, and it has earned its reputation because it reproduces the broad architecture of the modern cosmos. Clusters and filaments on huge scales, and a zoo of galaxies on smaller ones. But broad architecture is not the same as predicts the exact tempo. The first few 100 million years are where the story is most sensitive, because tiny differences early can become enormous differences later. If gas cools a little faster in some halos, you get stars earlier. If you get stars earlier, you get metals earlier. If you get metals earlier, you build dust earlier. If you build dust earlier, you change how light escapes, how it reddens, and how we measure what's there. The early universe is a feedback machine. Turn one knob and the downstream scene changes. So the real question isn't whether the universe could build quickly. It could. The question is whether it built as quickly as some of Webb's earliest images seem to imply, and whether the giants were truly giants or were being made to look that way by the physics of light, distance, and inference. Webb isn't weighing galaxies on a cosmic scale. It's collecting photons. Then we infer properties, mass, star formation rate, size, age, by matching that light to models of stellar populations and glowing gas. That inference is incredibly powerful, but at the redshift frontier, it's also vulnerable. Every data point is stretched by expansion, dimmed by distance, filtered through dust, and sometimes amplified by gravitational lensing. One wrong assumption in the model can turn a small object into a monster on paper. This is why, early on, the internet filled with the word impossible. Many of the first dramatic candidates were found through images alone. Photometric redshifts. Their colors looked like a strong Lyman break, hydrogen swallowing light below a threshold, suggesting extreme distance. Photometric redshifts can be excellent, but they can be fooled. A dusty galaxy that's actually closer can mimic the same colors. A pair of overlapping sources can masquerade as one, and bright emission lines from hot, ionized gas can land inside a broadband filter, boosting the brightness and making a galaxy look like it has far more starlight than it really does. Then comes spectroscopy, the hard test. Split the light, look for features, measure where they land, and pin down the redshift with far less ambiguity. Webb's spectrographs were built for exactly this moment, and they delivered. Some candidates were demoted, a few were reinterpreted, but several were confirmed as genuinely distant, genuinely luminous galaxies, existing only a few 100 million years after the beginning. That confirmation matters because it changes the debate from "are we being tricked?" to "what does this imply?" Here's the first implication that sounds boring until you feel it in your gut. The early universe is not only able to build galaxies quickly, it seems to have been building a lot of bright ones early. Not one freak, not one lottery winner, a measurable population that is brighter or more abundant at the bright end than many pre-Webb extrapolations expected for redshifts above 10. So why would the early universe be such an overachiever? Start with the most ruthless advantage: density. In the first few 100 million years, the universe was smaller. Matter was packed into less space. Gravity had a shorter distance to do its work. Gas streams were thicker. Encounters were more common. If the later universe is a city with wide roads and long commutes, the early universe is a crowded market where every stall is within shouting distance. In that environment, mergers don't feel like rare events. They feel like weather. And mergers do something specific. They compress gas. Compression triggers starbursts. Starbursts create huge numbers of hot, short-lived stars that pour out ultraviolet light. And that light, stretched by expansion into the infrared, is exactly what Webb is optimized to catch. Bright doesn't have to mean already mature. Bright can mean currently on fire. This leads to the second implication. Brightness is not mass. A small violent galaxy packed with newborn massive stars can outshine a much larger, calmer galaxy full of older stars. Think of it like fireworks versus a city skyline. For a few seconds, a tiny chemical burst can outshine an entire neighborhood of streetlights. If early galaxies are biased toward young, massive stars, their light-to-mass ratio changes. If the initial mass function, the distribution of star masses at birth, leans more top-heavy early on, you get more brilliant stars per kilogram of gas. That would make early galaxies appear too big in light, even if their true stellar mass is less outrageous. Then there's the question of the very first stars. Population 3. These stars formed out of nearly pure hydrogen and helium, without the heavier elements that make cooling easy. The expectation is that POP3 stars were massive, short-lived, and capable of producing intense radiation and huge supernovae. Whether we have seen them directly is still contentious, But the role they would play is not mysterious. They are cosmic accelerants. The first stars are the ones that turn a chemically simple universe into a universe that can cool gas efficiently, build dust, and assemble planets later. In a sense, the first stars are what makes the universe good at making more stars. If POP3 formation begins earlier in some regions or proceeds in denser clusters than we predicted, it could jumpstart enrichment and make subsequent star formation far easier. Dark matter is the other half of the engine, and it's the half we can't see. If dark matter, halos in the early universe, formed slightly earlier or concentrated mass slightly more efficiently, they would create deeper gravitational wells for gas to fall into. Deeper wells mean higher gas densities. Higher densities mean faster cooling and faster star formation. The difference between this halo collapses at 200 million years and this halo collapses at 300 million years is not just 100 million years. It's a head start in an exponential race. Now add a third ingredient: gas inflow along filaments. Galaxies don't only grow by smashing into neighbors, they also grow by being fed. In the early universe, cold streams of gas can flow along the emerging cosmic web, funneling fuel into young halos. A galaxy doesn't need to wait for a merger if the universe is already piping gas into it like a fire hose. And yet, even with all of that, the phrase "impossible galaxies" didn't catch on because of mild surprises. It caught on because some early analyses implied extreme stellar masses at extreme times, numbers that looked like the universe had assembled Milky Way scale stellar populations almost instantly. That would strain the simplest hierarchical timeline, because assembling that much stellar mass requires converting enormous amounts of gas into stars quickly and doing it without feedback from supernova and black holes blowing the gas back out. Here is the crucial nuance. The tension isn't a single object, it's the pattern. If Webb had found one ridiculously bright galaxy at a ridiculous redshift, you could treat it as a cosmic oddity, a rare peak in a distribution. The bigger shock is that Webb found multiple unusually luminous galaxies early on, enough that the census of brightness, the luminosity function, looked elevated at the bright end. In plain language, the early universe looked less empty than it was supposed to look. Now the story gets sharper, because this is where the giant idea splits into two different claims. Claim 1, there are bright galaxies very early. That claim is now solid. Webb has spectroscopically confirmed extremely distant luminous galaxies. These objects exist. Their light has been measured. Claim 2, those galaxies already have the stellar mass of the Milky Way. That claim is more delicate. Some candidates look very massive. Some early estimates were wildly high. But the masses come from model fitting, and the model fitting is where the early universe loves to mess with you. One way it messes with you is with emission lines. When star formation is intense, the gas around young stars glows in specific lines: oxygen, hydrogen, nitrogen, like neon signs in a fog. Those lines can sit right inside a broadband filter and boost the measured brightness. If you interpret that boosted brightness as stars alone, you inflate the stellar mass. Another way the early universe messes with you is with dust and age. A slightly dusty young galaxy can look redder. A redder spectrum can be misread as an older stellar population. An older stellar population implies more accumulated mass. One wrong step, dust mistaken for age, and the inferred mass balloons. And then there's lensing. Some of Webb's deepest views stare through galaxy clusters that act like magnifying glass in space. Lensing is a gift because it lets you see fainter objects than you otherwise could. But it's also a trap because you have to know the magnification to infer the true luminosity. If the magnification is uncertain, the true brightness is uncertain and the inferred mass is uncertain. So what's left after the smoke clears? A stubborn core of disruption. The early universe produced bright galaxies earlier than expected, and produced enough of them that theorists have to explain not just one anomaly, but a statistical shift. Models can respond in a few ways. They can make star formation more efficient at high redshift. They can adjust feedback prescriptions, how supernovae and black holes regulate gas. They can revise assumptions about stellar populations. They can refine how dust forms and how light escapes. Or they can question small-scale behavior of dark matter and early halo growth. None of these options require erasing the Big Bang. They require revising the detailed script of the first billion years. And because this isn't just about galaxies, it spills into a larger chapter. The early universe was supposed to be dim. If that were true, the dawn of the cosmos would look like a slow fade-in. Webb is hinting at something closer to floodlights, bright pockets of structure appearing sooner and in greater numbers than we expected to directly see. If those early bright galaxies were common, they also matter for cosmic rionization, the era when ultraviolet light from the first stars and galaxies stripped electrons from hydrogen and helped turn the universe transparent on large scales. If the early universe built more efficient light factories, the timing and texture of that transition shifts, changing the environment that later galaxies inherited. There's another layer to this that sounds like bookkeeping, but is actually the heart of the mystery. Time is brutally short. When you say 300 million years after the beginning, you're describing a universe that has barely finished its first act. That is enough time for gravity to pull dark matter into halos and for gas to form stars, yes. But it is not a lot of time for repeated generations of starbirth and death to cycle gas, enrich it, cool it again, and build the kind of complex, dusty, chemically mature systems we associate with later epochs. And yet, Webb is catching hints of maturity in some of these early systems. Strong line emission, unexpectedly bright continua, and in some cases signatures that suggest heavy elements are already present. The universe, in other words, did not just ignite quickly. It began polluting itself quickly. That pollution is what made everything after it possible. This is where the record-setting redshifts become more than trivia. When spectroscopy confirms galaxies at redshifts above 13 and 14, you are looking at objects whose light left when the universe was still in its infancy. In that era, the cosmic environment is supposed to be simple: hydrogen, helium, and a faint seasoning of lithium. The first stars are supposed to be the ones that change that recipe. If you then detect chemical fingerprints that usually require multiple stellar generations, you have to ask whether the first stars were more extreme than we modeled, or whether star formation in the first galaxies proceeded in bursts so intense that enrichment happened at high speed. Either way, the early universe starts to look less like a gentle beginning and more like an emergency response, a frantic conversion of gas into light before anything had a chance to settle. And while we're talking about settling, consider shape. Pre-Webb, many people imagined early galaxies as formless smudges, barely there, because that's all earlier telescopes could show us. Webb's resolution changed the conversation. It didn't just reveal that early galaxies exist, it revealed that some are compact, dense, and clumpy in ways that are hard to ignore. Compactness matters because density is destiny. If you pack gas and stars into a smaller volume, everything speeds up. Star formation becomes more efficient. Supernovae overlap. Outflows collide. The central regions can become nurseries and blast furnaces at the same time. A compact early galaxy can build a lot of stars quickly, not by being huge, but by being intense. This is also where active black holes sneak into the mass story. If a young galaxy hosts a growing black hole, that black hole can contribute to the light. It can make the galaxy look brighter than its stellar population alone would suggest. If you mistake some of that light as starlight, you inflate the inferred mass or star formation rate. Separating stellar light from black hole light at extreme distances is difficult, and it's another reason why early giant claims are constantly being revised. Webb helps because spectroscopy can reveal the fingerprints of accretion, but it doesn't erase the complexity. At the frontier, every galaxy is a composite of competing engines. So imagine what theorists are trying to do. They're not trying to match one image, they're trying to reproduce a population. How many bright galaxies exist at a given redshift? How quickly their number grows with time? How their sizes scale with brightness? And how their chemical signatures evolve? That's not a single knob. That's a control panel with 100 interacting switches. Change the star formation efficiency and you change feedback. Change feedback and you change how much gas remains. Change how much gas remains and you change future star formation and chemical enrichment. Change chemical enrichment and you change cooling and dust, which changes how light escapes, which changes what telescopes measure. In the early universe, observation and theory chase each other in circles like predators in a storm. And there's a fourth ingredient that's easy to overlook because it's invisible in every pretty image: selection. Webb can see incredibly faint things, but it still sees what it's pointed at. And early on, it was pointed where it would be maximally productive. Deep fields, lensing fields, and survey regions with existing multi-wavelength data. That means the first shocks arrived from the places most likely to contain them. Regions where lensing boosts the distant background, regions with repeated exposures that stack signal, regions pre-selected for cosmic archaeology. This doesn't manufacture early galaxies. It means Webb hit the richest soil first. The surprise isn't that rich soil contains fossils. The surprise is how many fossils were waiting and how complicated they already looked. If you want a single sentence that captures the technical tension without the drama, it's this: the observed abundance and brightness of some galaxies at very high redshift appear higher than many pre-Webb models predicted. That's the core. Everything else is interpretation. Now, interpretation has its own traps. One trap is assuming that star formation rate is a smooth dial. It isn't. Galaxies can breathe, they can inhale gas and then blow it out. They can spend tens of millions of years in a frenzy and then fall quiet, then flare again when a merger or inflow restarts the engine. When Webb catches a galaxy in its bright phase, it can look like the universe has been doing that non-stop, when in reality, we may be seeing a snapshot of an extreme moment. If early galaxies were bursty, the bright tail would be populated by short-lived fireworks. That would increase the number of bright detections without requiring every early galaxy to be massive all the time. It would mean the early universe was not uniformly productive. It was violently intermittent. Another trap is treating stellar mass as a simple sum. At high redshift, we often infer mass from light in the rest frame ultraviolet and optical, but those bands are affected by young stars, dust, and nebula emission. The features that best indicate an older, more massive population, subtle breaks and slopes in the spectrum, are harder to measure and easier to confuse. That's why the same object can swing from impossibly massive to still very bright but less outrageous as the data deepens. This isn't backpedaling. It's the normal process of turning first sightings into measured history. And yet, even if you downshift every exaggerated claim, Webb still leaves you with something that gnaws. Because even less outrageous is still outrageous when the clock is that short. It is outrageous to realize that, while our own galaxy was still a future idea, the universe was already building luminous systems and arranging them into the beginnings of large-scale structure. It is outrageous that we can confirm light from those epochs, analyze it, and watch theory scramble to keep up. It is outrageous because it forces you to accept that the Milky Way's greatness is provincial. It's the biggest thing in our sky because we're inside it, the way your neighborhood feels like the whole world until you look at a map. Webb is that map. But the scariest part isn't that the early universe was bright. It's what that brightness implies about speed. In cosmology, growth rates aren't linear. The amount of fresh gas a halo can pull in rises dramatically as you go back in time. The universe is denser, the dynamical times are shorter, and the inflow along filaments can be relentless. Picture a young galaxy not as a lonely island, but as a drain at the bottom of a funnel. Matter doesn't wander in, it pours in. When you have that kind of supply, the limiting factor isn't, is there enough fuel? It's, how violently can you convert fuel into stars before the engine blows itself apart? That's why feedback is the battleground. Supernovae and stellar winds inject energy into gas, trying to push it back out. Radiation from massive stars can heat and ionize the surrounding medium, making it harder for gas to collapse. If a black hole is feeding, it can drive outflows that cut off the supply. In many models, this self-regulation is what prevents small early galaxies from turning into runaway monsters. But self-regulation depends on environment. In a denser universe with deeper potential wells, feedback has a harder time escaping. Energy that would vent into space at later times may instead slam into surrounding gas, compress it, and trigger more star formation. The same explosion that quenches a galaxy in the modern era could, in the early era, simply rearrange the gas and light the next fuse. So, when Webb finds a surprisingly bright young galaxy, it's not necessarily a sign that physics broke. It can be a sign that the balance point between fuel and feedback is different at high redshift. The early universe may have allowed galaxies to run hotter before the thermostat kicked in. There's also a definitional trap in the word giant. Giant can mean stellar mass, it can mean halo mass, it can mean physical size, it can mean brightness. In the early universe, those properties do not track each other the way your intuition wants them to. A galaxy can be physically small, compact, even tiny, while being ferociously bright. It can have a modest stellar mass but a massive halo, or a massive halo but a stellar population so young that it temporarily looks like a beacon. It can be chemically young but photometrically old-looking because dust and lines distort the spectrum. If you don't separate these meanings, you end up arguing with yourself. This is why astronomers keep returning to the same brutal question. What are we actually seeing? Sometimes the answer is a galaxy whose gas is so excited that its emission lines are doing half the talking. And sometimes, uncomfortably, it's galaxy that really is building mass faster than we expected. Webb has also forced people to confront cosmic variance. The universe is lumpy. When you stare at a tiny patch of sky, you are not sampling the cosmic average. You are sampling one neighborhood. One neighborhood might be a rich node in the cosmic web, already overloaded with gas flows and early structure, and it will produce more bright galaxies than a random region. Another patch might be a void and look emptier. Early on, when deep fields covered tiny areas, it was possible that we were seeing a biased region and mistaking it for a universal truth. That's why survey strategy matters. As Webb observations spread across multiple independent fields, the pattern becomes harder to dismiss as a fluke. But the warning remains. The early universe doesn't distribute its surprises evenly. And remember the psychological trick here. We are looking back into an era where the universe is only a few % of its current age, but we are doing it with instruments and models built from a universe that is old and structured. We take for granted concepts like galaxy, stellar population, and metallicity as if they were stable categories. In the first few 100 million years, they may be more fluid. A galaxy at redshift 14 might be closer to a rapidly assembling complex of star-forming clumps than a settled system with a clean boundary. We might be applying modern labels to primordial chaos. That's why some of the most chilling hints in Webb's data are about composition, not just brightness. If some extremely early galaxies already show evidence of heavy elements, then the first stars didn't just exist. They lived, died, and enriched their surroundings fast. Heavy elements are the ashes of stellar furnaces. When you see them early, you're seeing a universe that has already been burning for a while. The darkness didn't last long. Now zoom out one step, and the implication becomes even sharper. If early galaxies are producing heavy elements and dust quickly, they can start hiding themselves. Dust absorbs ultraviolet and optical light and re-radiates it in the infrared. That means the early universe could contain a population of galaxies that are massive and active, but dim in the wavelengths we first used to search for them. Webb is sensitive in the infrared. But there are still regimes where other observatories, radio and submillimeter telescopes, are better at tracing coal dust and molecular gas. The early universe might be richer than Webb alone can map, and that possibility cuts both ways. It could explain why we're seeing bright galaxies, or it could hint that we're still missing whole classes of objects that change the statistics again. So, the giants question becomes a moving target. Webb is revealing one population and forcing us to rewrite the predicted abundance of that population. But it also raises the possibility that the census is incomplete and that the early universe is not just early, but crowded in ways we haven't fully counted. This is what makes the situation terrifying in the right way. Not because it means the universe is broken, because it means the universe is more capable than we assumed. More efficient, more aggressive. It builds structure quickly. Then it begins to self-modify through chemistry, dust, and feedback, changing the rules as it goes. And once you accept that, you can't unsee the consequence. Our galaxy is not the centerpiece of a slow story. It's one bead on a necklace that was already being assembled long before we arrived to notice it. And now, the insult, what this means for the Milky Way. We used to treat our galaxy as a baseline, an archetype, a large spiral with hundreds of billions of stars sitting at the center of our personal intuition about what a big galaxy is. Webb is forcing a reframe. The Milky Way is not the universe finding its footing. It is the universe continuing a process it had already been running for billions of years, clumping, igniting, merging, stabilizing, reorganizing. When you compare timelines, the humiliation becomes mathematical. The oldest stars in the Milky Way trace back to early cosmic times, but the Milky Way, as a coherent, large spiral, took time to assemble. Our galaxy's disk, the structure we emotionally identify as the Milky Way, is the product of long, relatively steady evolution. By the time our galaxy was pulling itself into something recognizable, the universe had already produced galaxies that were blazing, clustering, and in some cases already beginning to exhaust their most violent growth phases. And here's a thought experiment that lands like a punch. Imagine two cities. One is built slowly over centuries, roads laid, districts formed, neighborhoods stabilized. That's the Milky Way. Now imagine that, before your city even finished its first stone bridge, you receive photographs from across the ocean of megacities, already packed with towers and traffic, already ancient enough to have ruins. That's what these early luminous galaxies feel like. They tell you the universe was building at industrial scale before your local history even began. Even if some of those early galaxies turn out not to be as massive as the Milky Way, the fact that they are bright, chemically active, and present in large numbers that early still shifts the story. It means the universe didn't need 10 billion years to start acting complex. It started early, and it started everywhere. And if that's true, then the next scale up becomes the real shock, because galaxies are not the end of the hierarchy. They are the foundational bricks. The universe stacks them into neighborhoods, then into cities, then into continents of structure so large that the Milky Way becomes a rounding error. Where exactly is our galaxy sitting inside that architecture, and what is already pulling it? Right now, through a cosmic landscape that is bigger than anything we evolved to imagine. Because our galaxy is not parked. It's drifting, falling, being tugged and shoved through space like a leaf caught in an invisible river, and the river has banks you can't see. Start with the uncomfortable fact: you are moving right now, even if you feel perfectly still. Your planet spins. Your planet orbits. Your star circles the Milky Way. And the Milky Way itself is not simply sitting inside the universe like a photograph pinned to a wall. It is in motion relative to the oldest light we can observe, the cosmic microwave background. That ancient glow is the closest thing the universe has to a true rest frame, a backdrop left behind when the universe cooled enough for light to travel freely. And our motion against it shows up as a measurable dipole, one direction slightly hotter, the opposite slightly colder. Because we're plowing through it. The speed is not subtle. Our motion, relative to that background, is about 369 kilometers per second. Not kilometers per hour, per second. That's over 1 million kilometers every hour, and we feel none of it. You could live a full life, fall in love, build a family, forget your own childhood, and the Milky Way would still be racing through the universe at that pace like nothing happened. And that number is only the cleanest headline speed, the one tied to the microwave background itself. The local group's bulk motion through the nearby universe is on the order of 600 kilometers per second. The directions of these motions are not arbitrary. They are fingerprints of the mass distribution around us, visible and invisible, near and far, including mass hidden behind our own galaxy's dust. The strange thing is that we know this motion without ever leaving our galaxy, because the universe gives us two separate velocity fields to compare. One is the general expansion, the Hubble flow, where distance and recession, speed are linked on average. The other is the deviation from that average, the peculiar motion, the part caused by uneven gravity. To extract the peculiar part, astronomers need distances that don't come from redshift alone. They build distance ladders outward using standard candles and standard rulers, pulsing Cepheid variables in nearby galaxies. The glow of old red giant stars, the Tully-Fisher relation linking a spiral galaxy's rotation speed to its intrinsic brightness. The fundamental plane linking the size, brightness, and stellar motions of elliptical galaxies. Each method has its own weaknesses, but together they let you estimate how far a galaxy truly is. Then you compare how far it is with how fast its light is redshifted. If the galaxy is moving faster or slower than the expansion predicts, that difference is the signature of the gravitational terrain it's sliding through. Once you have enough of those signatures, the universe stops looking like dots and starts looking like weather. You can reconstruct the flow field and watch it stream towards certain regions and away from others. In that view, a supercluster isn't just a place where galaxies happen to be close together. It's a drainage basin in the cosmic weather system. That's why Laniakia's border is defined like a watershed line on a mountain range. Stand on one side and the rain runs to one river, step across and it runs to another. Galaxies are the raindrops and gravity is the slope. That is why your question is so sharp. Where are we? Sounds like an address. In cosmology, it is a vector. So start with the first layer of the address, the local group. The local group is our immediate gravitational family, a loose collection of galaxies bound together despite the overall expansion of the universe. If expansion is the tide that tries to pull everything apart, a group like this is a knot of gravity tight enough to resist the tide. The Milky Way and Andromeda are the two dominant bodies in that knot, and around them swarm dozens of dwarfs, small galaxies with faint stellar populations and huge dark matter halos relative to their starlight. Some are bright enough to make the history books, like the Large and Small Magellanic Clouds. Others are so dim they were only discovered recently and still feel like rumors until you see them plotted on a map. If you draw a circle around the local group, it spans roughly 10 million light-years. That number sounds abstract until you remember the Milky Way's bright disk is about 100,000 light-years across. 10 million is 100 Milky Ways laid end to end. And that's just our quiet suburb of the cosmos. Inside that suburb, the Milky Way's companions feel close enough to matter emotionally. The Magellanic Clouds hang in our sky as fuzzy smears because they are nearby enough to show structure. The Sagittarius dwarf is being torn apart and fed into our halo, its stars stretched into streams as gravity peels it apart. And Andromeda, roughly 2.5 million light-years away, is not just a neighbor. It is a future collision written in gravity, the kind of future you can ignore only because the timescale is billions of years. The local group is sometimes described as a dumbbell, a Milky Way lobe and an Andromeda lobe connected by a bridge of gravity. The center of mass sits somewhere between them. Everything else nearby arranges itself around that relationship, and the relationship is not static. While most galaxies in the larger universe recede from us as space expands, Andromeda is one of the rare major exceptions because gravity inside the local group wins locally. But the local group is not the end of the nesting doll. It's a tile in a larger floor. Zoom out and you enter the local volume, then the region historically called the Virgo supercluster, a broad arrangement of galaxy groups and clusters that includes us and the Virgo cluster, the nearest major cluster of galaxies. This is where neighborhood stops being a helpful word. You are no longer talking about a handful of galaxies. You are talking about geography, corridors of galaxies, regions of enhanced density, and the beginning of something that only makes sense when you stop thinking in terms of isolated islands and start thinking in terms of flows. In 2014, astronomers used galaxy velocity flows to define the boundaries of a structure far larger than the Virgo supercluster. They called it Laniakea, a Hawaiian name meaning immeasurable heaven. And it is a statement of scale more than poetry. Laniakea is not a tidy ball of galaxies. It is a basin, a region of space where galaxy motions converge like rainwater funneling into a watershed. Its boundary is defined by a surface. Cross that surface and galaxies no longer flow toward the same gravitational sink. They flow toward different sinks. In that definition, a supercluster isn't simply where galaxies are, it's where galaxies are going. Laniakea spans roughly 160 megaparsecs, about 520 million light-years. Within it are on the order of 100,000 galaxies. Those numbers are not meant to be memorized, they are meant to hurt. Because once you place the local group inside Laniakea, the Milky Way becomes what it truly is in the cosmic census, one spiral among 100,000, riding a current in a basin so wide that light takes more than 500 million years to cross it. Laniakea also carries a psychological trap, because its name makes it sound like an object you could point to in the sky. It is not. You don't see Laniakea the way you see Andromeda. You infer it the way you infer the shape of a valley in fog by watching which way water runs. That is why its shape is irregular, and why its center is defined by flow convergence rather than a single bright beacon. In the flow map, our local group is not near the deepest part of the basin. We sit closer, to an edge like a town built on the slope of a watershed rather than at the mouth of the river. That matters because edge regions feel calmer. The deepest basins are where galaxies pile up into rich clusters, where hot intracluster gas strips smaller galaxies and turns spirals into featureless ellipticals over time. Living near the edge of a basin is one reason we still recognize our galaxy as a spiral at all. Now you can feel the real insult. The Milky Way is not the main structure. It is not even the main structure in its own neighborhood. It is a single member of a gravitational watershed, drifting with everything else inside a flow field shaped by mass on scales your brain has no instincts for. And that leads directly to the second half of your question: what is already pulling it right now? The earliest version of the answer was simple: the Great Attractor. Astronomers noticed decades ago that our local group is moving in a way that doesn't neatly match the smooth Hubble expansion. Nearby galaxies have velocities that, when you subtract the general expansion, still show a coherent drift. It's like watching leaves on a lake. Even if the water level is slowly rising, the leaves can still be sliding toward a drain. When astronomers mapped that drift, they found that many galaxies in our region of the universe seem to be streaming toward a particular direction in the sky. That direction lies uncomfortably close to the plane of our own Milky Way, in a dusty band that hides the background universe from optical view. This is the zone of avoidance, and the name is as literal as it sounds. For generations, our galaxy's dust made a strip of the external universe difficult to see, like trying to study the horizon while staring through a sandstorm. The irony is vicious. We want to understand what's pulling our galaxy, but our galaxy itself hides part of the answer. The Great Attractor's most unnerving feature is that it was real before it was seen. It entered astronomy as a gravitational rumor, a direction in which many galaxies seem to have an extra drift, a coherent bias in their velocities that couldn't be explained by the smooth expansion alone. The name stuck because it captured the emotional reality of the discovery. Something massive was influencing us from behind a curtain. The curtain is our own disk. The Milky Way's plane is crowded with stars and laced with dust. Optical telescopes looking through it are blinded and reddened, and distant galaxies hide behind that glare like fireflies behind a headlight. That is why the zone of avoidance matters. It's not merely a missing strip on a chart, it's a missing strip in the gravitational accounting of our neighborhood. If you can't see what's there, you undercount the mass. If you undercount the mass, you misunderstand the flow. When astronomers finally punched through that curtain with longer wavelengths, one of the structures that emerged was the Norma cluster. It is a rich cluster with a mass on the order of a quadrillion suns, packed with hundreds of galaxies and embedded in a larger concentration of matter. Photographs of it are almost insulting. A field of foreground Milky Way stars, sharp and bright, with a distant swarm of galaxies behind them. as if the universe is reminding you that your home is both the observer and the obstruction. Norma's position in the zone of avoidance is one reason the Great Attractor long felt like a mythic monster. The monster was always there. We were staring through our own fog. Behind that storm lies a concentration of mass large enough to dominate local flows. The Great Attractor is not a single object you can point to and say, "There." It is a region anchored by massive clusters, and Norma is one of its key landmarks. The distances involved are staggering, but still local in cosmic terms, roughly a couple hundred million light-years. Within that range, a rich cluster's gravity can influence the motion of galaxies across a vast volume of space. The Great Attractor earned its name because it appears to dominate our region's drift, pulling whole groups and clusters inward. And the farther you extend the map, the less comfortable the Great Attractor becomes as a single explanation. Beyond it lies Shapley, a concentration of clusters so rich that even at vastly larger distances, it still registers in the flow field. Imagine realizing that the thing pulling you is itself sitting in the gravitational shadow of something even larger, farther out, heavier, and still shaping the drift of galaxies across hundreds of millions of light-years. The Great Attractor stops being the final answer and becomes the nearer bend in a much longer river. That is what makes the push concept so important. Overdensities attract, that is intuitive. But underdensities carve the landscape too. A void doesn't have to do anything dramatic. It only has to flow map. The dipole repeller sits like an hourglass, with the dipole repeller at the center. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on the flow, creating a whirlpool effect. The dipole repeller is a massive object that pulls on flow map. The dipole repeller sits like an unseen lowland, a direction from which the local universe appears to be streaming outward. It is difficult to photograph for the same reason darkness is difficult to photograph. You can only prove it by showing what isn't there, and then by showing what everything else is doing as a result. A large underdense region, identified through the velocity field, was nicknamed the dipole repeller. The name sounds theatrical, but it captures a real idea. Our motion is influenced not only by attraction toward overdensities like Shapley, but also by motion away from emptiness. You are being pulled toward mass and pushed away from a deficit of mass at the same time. Not metaphorically, kinematically. Your galaxy is a boat in a current shaped by mountains of matter and valleys of nothingness. This is why where we are is inseparable from where we're going. The Milky Way's address is not a dot on a static map. It is a trajectory through a dynamic landscape. Now widen the lens again, because the true architecture is bigger than any named supercluster. Laniakea itself is only one basin in a larger network. On the biggest scales we can map, galaxies are not scattered randomly. They trace a cosmic web, filaments of matter stretching across hundreds of millions of light years, intersecting at dense nodes where clusters live and separated by vast voids where galaxies are rare. This structure emerges naturally when gravity amplifies tiny early fluctuations and matter collapses into a frothy pattern. If you could drain the universe of light and look only at the skeleton of mass, it would resemble a three-dimensional neural network, strands and knots, with huge cavities between them. The cosmic web is the grand version of that same logic. On human scales, you think of empty space as neutral. On cosmological scales, empty is an active player because gravity treats the universe like a sculptor treats clay. It pushes matter into ridges and leaves hollows behind. Filaments are not ropes you could touch. They are regions where the density is slightly higher than average, but slightly across 100 million light-years is enough to trap galaxies and funnel gas. Clusters form at the intersections because that is where multiple filaments feed the same node, piling mass up until it becomes a gravitational sink. Voids form between filaments because matter has been drained out of those regions into the surrounding ridges. This is also where dark matter becomes unavoidable without even mentioning it by name. The Webb's skeleton is mostly invisible mass. The galaxies you see are the frosting. The gravitational wells that guide the flows are dominated by matter that does not emit light. That is why flow maps and lensing maps are so valuable. They are ways of seeing the unseen by watching what it does. When you say the Milky Way is being pulled and pushed through a cosmic landscape, you're really saying that your galaxy is surfing on the curvature of space-time created mostly by things you cannot photograph directly. This web is not decorative. It is the universe's load-bearing structure. Filaments are where gas flows. Nodes are where clusters grow. Voids are where matter is thinnest. In the web, locations determines supply. A galaxy embedded in a dense environment is constantly harassed by neighbors and bathed in hot cluster gas. A galaxy in a quiet filament has access to inflows without constant disruption. A galaxy on the edge of a void is starved of neighbors and interactions but can drift along gentler currents. Our local group sits on a small thread of that web, not near one of the most massive nodes, but in a quieter region where the nearest giant clusters are distant enough that we aren't constantly being torn apart by their environment. That quiet has consequences. It is one reason the Milky Way still has a disk and still forms stars. It is one reason our group contains two major spirals instead of being dominated by a single gigantic elliptical that has swallowed everything around it. In the cosmic web, environment is fate. Voids can be so large that the numbers start to sound like a mistake. A void, 100 million light-years across, can swallow thousands of Milky Ways and still feel empty. The largest underdensities mapped in modern surveys reach radii of hundreds of millions of light-years, and when you place those against the Milky Way's 100,000 light-year disk, you realize the ratio is not big, it is humiliating. If you were a civilization trying to navigate with galaxies as landmarks, entering a supervoid would feel like losing the sky. Your nearest bright neighbors would be so far away that the universe would look thin, washed out, almost abandoned. The cold spot line of sight is famous because it ties this geometry to the oldest light in the universe. The cosmic microwave background is a relic signal from the early universe, and the cold spot is an anomaly in that relic sky. Along that direction, galaxy surveys have traced a significant underdensity, and one mechanism that connects a large void to a CMB feature is the integrated Sachs-Wolf effect, which arises because the universe's accelerated expansion changes gravitational potentials over time. Photons passing through evolving potentials can emerge with slightly altered energies, imprinting subtle temperature shifts on the CMB. You don't need the math to feel the implication. Empty space itself can leave fingerprints on the oldest light we can see, and now notice what that means for the Milky Way's motion. A void doesn't just sit there, its emptiness shapes the flow. Filaments feed nodes, nodes pull along filaments, voids drain into filaments by failing to hold galaxies back. On these scales, the universe behaves less like a collection of objects and more like a field of gradients. Your galaxy is not choosing a path, it's following the slope. So when you ask what is pulling us right now, the clean answer is the universe is. Mass concentrations like the Great Attractor region and the Shapley concentration define one side of the story. The pull toward dense nodes. Underdense regions like the dipole repeller define the other, the push away from emptiness. Together, they set the direction of our peculiar motion through the expanding cosmos. And on top of that motion sits the broader expansion itself, stretching the entire web outward, even as gravity tries to tighten it locally. This is the part that should make your throat tighten, because it forces you to imagine your galaxy as a tiny thing inside a machine whose moving parts are too large to picture. We're used to thinking of our galaxy as the stage and the rest of the universe as the backdrop. In reality, the Milky Way is a prop on a set that is being dragged across space by forces whose sources were hidden behind our own dust until very recently. And that returns us to Webb, because Webb's gift is not only distance, it is clarity through obstruction. This is why the zone of avoidance is more than an observational inconvenience. It is a blindfold placed by our own home. For centuries, we built cosmic maps with a strip missing, then tried to explain the motion of our galaxy with that incomplete map. Radio astronomy began the repair by using the 21-centimeter line of hydrogen to trace gas through dust. Near-infrared surveys expanded the catalogue of hidden galaxies by catching starlight that dust cannot completely block. Space telescopes added precision by escaping Earth's atmosphere. Every step reduced the unknown. Webb is the newest blade in that slow surgery. Its strength is not that it can cover huge swaths of sky quickly. It can't. Its strength is that when you aim it at a dusty region or a distant lensed background, it doesn't just detect a smear, it resolves structure. It separates crowded sources, it captures spectra that pin down distances and compositions. In the context of our address, Webb's role is to make the obscured parts less mythical. It makes the hidden clusters behind the Milky Way's plane look like real places with shapes, members, and measured properties. The Great Attractor stops being a ghost story and becomes what it always was, a region of mass in a particular direction that our galaxy's motion has been responding to all along. When you look toward the zone of avoidance in visible light, you see the Milky Way's own stars and dust. When you look toward it in radio, you can begin to trace the galaxies behind. When you look toward it in infrared, you can peel back more layers. Instruments like Hubble have been used to image key pieces of the Great Attractor region, including the dense Norma cluster, helping turn a mythic name into a mapped structure rather than a pure inference. Webb is not a wide-field survey machine, but its infrared sensitivity is a scalpel. It can cut into dust-obscured regions to reveal galaxies and structure that would otherwise be hidden in the glare and haze of our own disk. That matters because every improvement in what we can see behind the Milky Way improves our map of the gravitational landscape that is moving us. The Great Attractor wasn't discovered as a single object. It was inferred from motion. It was named from effect. And only gradually has the cause been filled in with catalogued mass. As the zone of avoidance becomes less of a blind strip, our understanding of why we're moving becomes less guesswork and more geometry. Now let the full address land. You are in a spiral galaxy about 100,000 light-years wide. That galaxy is one of two giants in a loose group of more than 50 galaxies spanning about 10 million light-years. That group is part of a larger basin, hundreds of millions of light-years across, defined not by edges you can photograph, but by the direction galaxies flow. That basin is stitched into a cosmic web that spans the observable universe, a structure dominated by filaments and vast voids, and your entire filament is sliding through space, tugged toward dense concentrations and nudged away from underdense regions, while the expansion of the universe stretches the whole pattern outward. That is the architecture. That is the pull. That is the push. And here is the part most people never internalize. This flow is not a background detail. It is the environment your galaxy grew up in. A galaxy is not just a pile of stars that happens to exist somewhere. It is a long negotiation between gravity and gas, between supply and feedback, between the violence of encounters and the quiet of isolation. The cosmic web is the negotiation table. In a dense node, galaxies live in traffic. They pass close, tug on each other, strip gas, trigger bursts of star formation, then get quenched as hot cluster gas and black hole feedback shut the engines down. In that environment, spirals don't stay spirals forever. They get battered, their disks heated and scrambled, their gas removed until what remains is a smoother, redder system dominated by older stars. In the deepest nodes, one galaxy often ends up at the center like a king in a crater, growing by eating whatever falls in. It doesn't have to chase its meals. The web delivers them out on quieter filaments, and in the outskirts of basins, the story changes. Encounters are rarer. Gas can settle into disks instead of being constantly shocked. Star formation can continue for longer. You get galaxies like ours, organized enough to build stable orbits, calm enough to let planetary systems survive for billions of years, active enough to keep making new stars instead of shutting down early. The Milky Way's spiral. Arms are not just a feature of its mass, they are a feature of its address. And then there are the edges and the shadows, the places where the web's supply lines run thin. In those regions, you can get galaxies that are almost paradoxes, systems spread across huge volumes of space, but so faint that if you didn't know what to look for, you'd mistake them for nothing. Ghost galaxies. low surface brightness smears held together more by invisible mass than by the stars you can count. They are proof that galaxy is not a single template. It is a spectrum of outcomes sculpted by where the Webb fed you, where it starved you, and what kind of violence it allowed you to survive. Once you see the Milky Way as a product of this terrain, the fear shifts. It's no longer just that we're small. It's that we're living inside a machine that manufactures galaxies in wildly different forms depending on where they land in the flow. And the next step in this journey is to walk for millions of light years. The same Webb for millions of light years. The same Webb that keeps our spiral intact also forges those monsters in the densest cluster cores too. And once you truly accept that our galaxy is just one particle in a moving field, you can finally ask the next, more terrifying question, because the cosmic Webb doesn't only move galaxies, it sculpts them. It decides which ones grow fat and which ones get starved, which ones become tidy spirals and which ones get shredded, which ones become monsters at cluster centers, and which ones become ghosts so diffuse they almost don't exist. So what does the cosmic Webb build at the extremes? Galaxies so faint you can barely prove they're there, and galaxies so vast that the Milky Way would vanish inside their halos like a spark swallowed by fog? Because the cosmic Webb doesn't just place galaxies, it manufactures extremes. On one end of the spectrum are ghosts, galaxies spread across Milky Way scale footprints, but with so little starlight per square arc second that they look like smudges of background noise. On the other end are monarchs, central cluster giants that have spent billions of years at the bottom of a gravitational well, growing by merger after merger until their outer light dissolves into a haze shared with the entire cluster. That contrast isn't trivia, it's the Webb revealing its rules. Where you sit in the Webb determines whether you get fed, battered, stripped, inflated, quenched, or crowned. Start with the ghosts, because they teach the cruelest lesson. Invisible does not mean absent, it can mean diffuse. Ultra-diffuse galaxies are some of the most unnerving objects in modern astronomy, because they force you to stop equating galaxy with bright. A classic spiral announces itself with a crisp silhouette. An ultra-diffuse galaxy refuses. It occupies a large volume, often comparable in apparent size to much more massive galaxies, but its stars are spread so thin that the galaxy's surface brightness drops below what most surveys were designed to catch. In practical terms, that means you can stare straight at a galaxy and never know it's there, the way you can stare at fog and miss the outline of a mountain behind it. For decades, our catalogue of galaxies was biased toward what pops: bright cores, high contrast, objects that survive quick exposures and imperfect background subtraction. Low surface brightness systems are the opposite of that. They are fragile in data. A minor calibration error can erase them. A small amount of scattered light can drown them. A telescope's internal reflections can imitate them. The sky itself, airglow, zodiacal light, unresolved stars, fights you. To detect something like that, you don't just take a picture. You do a kind of forensic accounting. You model the sky background until it becomes a surface you can subtract. You remove the scattered light halos of bright stars that spill across your frame like oil on water. You track gradients that come from optics rather than the universe. You stack exposures so that random noise averages down while real, coherent structure stays. You ask whether a faint smear repeats in independent observations, whether it shifts the way a real object should, whether its shape survives different processing pipelines. And even then, you hesitate, because the difference between a galaxy and a processing artifact can be a few photons spread across thousands of pixels. Ultra-diffuse galaxies live right on that knife edge, which is why the first time you truly internalize them, it changes how you trust every image you've ever seen. So the ghosts weren't discovered late because the universe hid them out of spite. They were discovered late because our methods were tuned to a different kind of signal. Think about how cruel that is as a principle. We build a definition of galaxy from what we can easily detect. Then we treat that definition as reality. Then a new instrument comes along and shows us a category that violates our intuition, and suddenly the definition has to widen. Not because the universe changed, but because we finally admitted that faint was never the same as rare. That changed when astronomers started building surveys that treated faint, extended light as the target, not the nuisance. When those surveys turned toward dense cluster environments, the results were embarrassing in the best way. They revealed that entire populations had been sitting in front of us, whispering while we kept listening for shouts. The Coma cluster is the most famous example because Coma is what a rich node in the Webb looks like nearby, a gravitational city where galaxies live in traffic. In 2015, a low-surface brightness optimized campaign reported dozens of ultra-diffuse galaxies in Coma, objects with large effective radii but low stellar mass, first as a shock, then as a warning. Soon after, deeper and wider analyses using different data and selection criteria pushed the count far higher. One widely cited study reported 854 ultra-diffuse galaxies within the Coma cluster field they analyzed, implying that the true population could exceed 1,000 when you account for coverage and completeness. Coma is also the perfect environment for these ghosts to matter because a cluster is a stress test. In a quiet field, a faint, diffuse galaxy can drift for a long time without being disturbed, and you might never notice it because nothing dramatic happens. In a cluster, everything happens. Tidal fields are strong, encounters are frequent, gas stripping is routine. If ultra-diffuse galaxies can survive there, they are not fragile accidents. They are either protected by substantial, dark halos or continuously replenished by processes that create them. Either interpretation is uncomfortable. It means the Webb can create large, stable gravitational systems that produce almost no starlight, or it means the Webb can repeatedly manufacture diffuse galaxies as a byproduct of cluster violence. And here's the psychological sting. If a cluster can contain hundreds of galaxies that were effectively invisible to older surveys, then every conversation about typical galaxies is contaminated by selection. We used to build our intuition from the bright few, then wonder why models didn't match the statistics. But the statistics were incomplete. The universe wasn't refusing to behave. We were sampling the loudest members and calling them the population. The ghosts are the correction, and corrections are always humiliating. The jump from 40-something to 800 plus is the kind of escalation you normally associate with mistakes. But here, the escalation is the point. It's what happens when you stop looking for galaxies as bright knots and start looking for them as extended, barely there gradients. It's the difference between searching the ocean for islands by scanning for city lights and searching it by measuring tiny changes in the surface of the water. Now imagine what that means for empty. Imagine how many times in the history of astronomy we have looked at a dark patch of sky and called it nothing. Deep fields already humiliated us by turning nothing into thousands. Ultra-diffuse galaxies add a second humiliation. Even when a galaxy is nearby and large, you can still miss it if the light is spread thin enough. Emptiness is often an artifact of your detection threshold. And once you accept that, the early universe starts to feel even more crowded than Webb's images already suggest, because the distant universe is not only faint, It's faint in the most dangerous way. It is faint per unit area. A small, compact galaxy can be bright even if it's low mass, because its light is concentrated. A diffuse one can be massive enough to matter and still disappear, because its light is diluted. That brings us to the next, more frightening layer of the ghost story. The ghosts aren't only hard to see, they're hard to weigh. If an ultra-diffuse galaxy is truly extended and truly long-lived, it has to be held together by something. Stars alone, spread that thin, often can't provide enough gravity. So either the system is transient, an object caught in the act of being shredded, or it lives inside a dark matter halo massive enough to bind it. Many ultra-diffuse galaxies appear consistent with that second option. Gravity-rich, light-poor systems like enormous empty shells. This is where the Webb's fingerprints become obvious. A halo can exist without a luminous disk. A deep potential well can exist without a bright skyline. The Webb can build the scaffold and then, for whatever reason, feedback, stripping, starvation, fail to hang much starlight on it. That is how you get a galaxy that can span a region comparable to the Milky Way while holding only a few 100 million stars. It's a system that occupies the same real estate but lives on a different budget. So what are these objects really? There probably isn't one answer, which is the universe's favorite way to be unsettling. The same category can be produced by multiple histories. Some ultra-diffuse galaxies may be failed large galaxies. They formed in halos that were big enough to grow into something more luminous, but an early burst of star formation and supernova feedback could have heated and expelled gas before it turned into many stars. The halo remained, the potential remained, but the fuel was gone. Others may have formed with unusually high angular momentum, spreading their gas out so thinly that it never reached the densities needed for efficient star formation. Same mass, reservoir, different distribution, different outcome. In a cluster environment, there is an even harsher pathway: stripping. As a galaxy falls into a rich cluster, it doesn't enter a vacuum, it enters hot intra-cluster gas. Moving through that medium can strip away the galaxy's own gas by ram pressure, removing the fuel for future stars. At the same time, repeated tidal encounters with other galaxies and the cluster's overall gravitational field can heat and expand the stellar component. A system that might have been a compact dwarf outside the cluster can be puffed into a diffuse smear inside it. Harassment doesn't need to destroy a galaxy to change it. It only needs to keep kicking it until its structure inflates. And then there's the controversial angle: systems whose internal motions, based on the velocities of their stars or globular clusters, suggest unusually low amounts of dark matter compared to expectations. The headline version of that claim, a galaxy with no dark matter, spreads because it feels like heresy. The careful version is more honest. Some galaxies show unusually low inferred dark matter, but the inference is sensitive to distance, measurement technique, and the assumptions you make about how a faint system is oriented and supported. Change the distance, and you change the intrinsic luminosity and size. Change the tracer population, and you change the inferred mass. This is why the phrase, "no dark matter," is a trap. It turns a sensitive inference into a certainty, when the real story is about how close these objects sit to the limits of what we can measure. The NG C1052-DF2 saga became famous precisely because it exposes that fragility. The claim wasn't that dark matter can be photographed and was missing. The claim was that the measured velocity dispersion of the tracers was low compared to what standard halo expectations would predict for an object of that size and brightness. That's an argument about inference. It lives and dies on distance estimates, on the membership of globular clusters, on the statistical treatment of small samples, and on the question of whether the system is in equilibrium. In this corner of astronomy, you can change the conclusion by changing the assumptions you are forced to make, because the data is inherently sparse. But whether a given ultra-diffuse galaxy is halo-dominated, harassment-inflated, or dark matter-odd, the category as a whole delivers the same message. Galaxies are not guaranteed to be luminous. The cosmic web can create systems that occupy vast regions of space while barely announcing their presence. If we can miss those nearby, we have to respect the possibility that the distant universe contains analogous populations, faint, diffuse, numerous, and undercounted. And that possibility matters for everything Webb is doing. The most common picture people carry away from a Webb deep field is, look at all these galaxies. The deeper truth is, look at what we used to miss. Webb is not a wide-field survey machine, but its infrared sensitivity and sharp resolution push detection thresholds into regimes where faint, small, and distant galaxies become measurable. Every time that threshold shifts, the universe's inventory swells. The cosmos doesn't become more crowded, we just stop being blind to some of its residents. This is why the 2 trillion galaxies estimate makes sense as a mood even when it remains an extrapolation as a number. It isn't a claim that someone counted to 2 trillion. It's the recognition that the faint end dominates populations and that our instruments historically clipped the faint end off the distribution. Ultra-diffuse galaxies are one local proof that the faint end is not hypothetical. It is populated. Now swing the camera to the opposite extreme, where the cosmic web doesn't hide galaxies. It overfeeds them. In the densest nodes of the web, rich clusters. Galaxies don't live quiet lives. They fall inward along filaments. They orbit, collide, graze, merge, and strip each other. Gas gets heated into intracluster plasma, a hot medium that can strip the gas from infalling spirals, like a storm ripping leaves from a tree. Star formation can be triggered in bursts and then quenched as the fuel is exhausted or removed. Disks get heated and scrambled. Over time, a cluster acts like a blender. It takes ordered spirals and turns many of them into smoother spheroids. At the center of that blender sits the deepest well, the gravitational bottom where matter piles up. That is where you tend to find the brightest cluster galaxy, a giant elliptical or CD galaxy that grows by eating what the cluster delivers. It doesn't need to hunt. The Webb funnels prey toward the center. These central giants are some of the most extreme star systems in the universe, and they break your intuition in a different way than the ghosts do. Ghosts are large but faint. Cluster center giants are large and overwhelming, not necessarily because their cores are impossibly bright, but because their halos can extend into regions where the boundary between galaxy and cluster becomes a debate. This is why the phrase largest galaxy is always slippery. In a spiral, you can point to a disk edge where starlight drops rapidly. In a brightest cluster galaxy, the light can fade gradually into intracluster light. Stars that are no longer cleanly bound to one galaxy, but drift in the cluster's potential. If you measure to one surface brightness threshold, you get one size. If you chase the halo farther, you get another. The border is not a wall, it is a gradient. This is also why cluster environments matter so much to Webb's story. Remember, SMACS 0723, the first deep field that poured galaxies across a tiny patch of sky. That image is not just a gallery of distant systems, it's a demonstration of what cluster mass does. The same gravity that bends background Galaxies into arcs is the gravity that builds the cluster's internal hierarchy. It strips, it merges, it feeds the center. A cluster is both a lens and a furnace. It magnifies the distant universe for us, and it grinds its own member galaxies into new shapes over billions of years. In a rich cluster, you can almost see the assembly of a monarch as a slow crime scene. A spiral falls in along a filament, still blue with star formation. The intracluster medium strips its gas. The blue fades. Encounters tug at its disk. The disk thickens. A merger distorts it. Stars get flung outward. Tidal streams bloom like shredded fabric. Those streams don't vanish. They become part of the diffuse halo around the center. Repeat that hundreds of times and you get the extended envelope that makes brightest cluster galaxies so hard to define. The edge becomes the point where the last torn stars fade into the shared glow of the cluster. That shared glow, intracluster light, is the cluster. Wearing the remains of the galaxies it has processed. So when someone says a galaxy millions of light years across, the real meaning is a Webb node so dense and so old that the difference between a single galaxy and the cluster's collective star field starts to blur. It's not a carnival trick, it's a physical outcome of repeated mergers in a deep potential well. And that gradient is not a technical footnote. It is the actual cosmic violence made visible. The outermost stars of a central cluster giant are often the leftovers of disrupted galaxies, stars torn from smaller systems during mergers and tidal interactions, then redistributed into a diffuse envelope. In that sense, the halo is a graveyard. It's the afterimage of hundreds of separate histories dissolved into one. IC1101 is the famous name that gets passed around as a symbol of this extreme. It sits at the center of the Hubble 2029 cluster and is often described as among the largest known, brightest cluster galaxies. Depending on how you define the edge, descriptions of its extent can sound almost obscene. But even if you strip away the most sensational versions and hold on to the responsible framing, among the largest known, with size depending on definition, the comparison remains violent. A galaxy like ours, with its orderly disk and recognizable arms, becomes the kind of structure you could tuck inside the inner region of a cluster giant and still have room to spare for the halo's faint outskirts. Here's why that matters to the theme of tiny. When you compare the Milky Way to a central cluster giant, you are not just comparing two galaxies, you are comparing two addresses in the cosmic web. Our galaxy formed and evolved in a relatively quiet part of the web, a small group away from a rich cluster core with fewer catastrophic interactions. That environment preserved our disk. It allowed gas to remain. It allowed star formation to continue for billions of years instead of being quenched early by cluster conditions. The Milky Way's recognizable spiral structure is not merely a product of its mass. It is a product of its neighborhood. A central cluster giant is the opposite. Its neighborhood is violent. Its neighborhood delivers mergers. Its neighborhood strips gas from others and feeds debris into the center. Over billions of years, that environment erases disks and builds halos. The galaxy becomes a monument not because the physics is different, but because the supply lines are. So the cosmic web builds ghosts when it starves or inflates systems into low surface brightness, and it builds monarchs when it feeds the center of a node with a continuous diet of mergers. The extremes are the web's fingerprints. Now, bring the horror home. The Milky Way feels stable because the timescales are huge, but stability is not permanence. Our galaxy is an organized disk now. Yes, it still forms stars now, yes. It still has spiral structure now, yes. But in the local group, there is a future written in gravity, the relationship between the Milky Way and Andromeda. For a long time, the collision was treated as destiny, a near-certain event in roughly 5 billion years. More recent modeling, incorporating updated observations and the influence of other massive local group members, has emphasized that the future is less deterministic than the simplified story. The chance of a Milky Way-Andromeda merger over the next 10 billion years has been argued to be closer to a coin flip, with outcomes depending sensitively on masses and transverse motions, and on the gravitational influence of satellites like M33 and the Large Magellanic Cloud. That uncertainty doesn't make the story less intense. It makes it more honest and more eerie. The Milky Way's future identity as a spiral is not guaranteed. It depends on a gravitational dance with error bars. If a merger does occur, it will be slow and transformative, not a head-on crash of solid objects, but a long gravitational entanglement. Tidal forces will stretch both disks, pulling out tails of stars. Gas clouds will compress and collide, likely triggering bursts of star formation. Orbits will be scrambled. The central black holes, over time, would sink toward each other and eventually merge. The final product is expected to be a more spheroidal galaxy, less a pinwheel, more a smooth ember, because repeated mixing tends to erase the organized rotation of disks. In other words, even in our quiet corner of the Webb, the Milky Way is not immune to the processes that build cluster giants. We won't become a monster like a brightest cluster galaxy because we don't live in a rich cluster core with endless infall. But we may still lose the thing that makes us visually iconic, the spiral disk. And while that transformation is playing out on local timescales, the universe on the largest scales is doing something even colder. It is isolating us. The observable universe is not the whole universe. It is the part of reality that has had time to send light to us. Because the universe has been expanding while light travels, the proper distance to the edge of the observable region is more than 46 billion light-years in every direction. Even though the universe's age is about 13.8 billion years, that boundary is often discussed as a particle horizon, the limit of what we can see by light since the beginning. It's easy to get lost in horizon vocabulary, so here's the one thing that keeps it honest. These boundaries are not about our engineering, they're about geometry. A Hubble sphere is often described as the distance at which recession, due to expansion, would match the speed of light at this moment. That sounds like a wall, but it isn't. The expansion rate changes with time, and light can cross that sphere in either direction depending on the universe's history. The Hubble sphere tells you something about a present-day flow. It doesn't tell you what is forever unreachable. The particle horizon is the limit of what has had time to send light to us since the beginning. It defines the observable universe. It's the reason deep fields work at all. The sky is a record because light had time to arrive. The event horizon in an accelerating universe is the colder limit, the boundary beyond which events will never be able to affect us, even in the infinite future. That's the one that turns the sky into a shrinking archive. Over vast time, more regions cross from distant but visible into distant and causally disconnected. The universe doesn't hide them with dust, it hides them with expansion. What makes this so unsettling is that it turns our era into a kind of temporary privilege. We live at a time when the universe has had enough time to build a huge population of galaxies, but not enough time for accelerated expansion to isolate us from most of them. We live in the overlap window where the cosmic record is still readable. That window is wide on human timescales, but it is not guaranteed on cosmic ones. In the far future, the same physics that allowed Webb to look back almost to the first galaxies will make it harder and harder for anyone to look outward at all. A future astronomer could inherit a sky so empty that the story of the Big Bang would be much harder to reconstruct from observation alone. In that sense, Webb is not just showing us the past, it is preserving a view that will eventually become inaccessible. A photograph taken before the museum closes, and we are seeing it now. But in an accelerating universe, there is a second boundary that matters emotionally: an event horizon. Beyond a certain distance, events will never be able to affect us, even given infinite time, because the expansion of space accelerates. Light emitted beyond that horizon in the far future will never reach us. Over extremely long times, more and more galaxies slip beyond causal contact. The sky empties, not because galaxies disappear, but because the universe stretches the Webb until distant nodes fall beyond the horizon of influence. This is where Webb's deep fields become something more than pretty images. They become time-sensitive evidence. We live in an era when the cosmic web is still visible enough for us to reconstruct it, when the universe still provides external landmarks in abundance. A civilization in the far future, living inside the remnant of our merged local group, could look up and see a lonelier cosmos with fewer galaxies visible and far less observational leverage to infer the universe's origin story. The same expansion that lets us see far back in time also ensures that, in the deep future, much of the universe's history becomes inaccessible again, not by forgetting, but by geometry. So, yes, the Milky Way is tiny. Not because its star count is small, but because the universe's hierarchy is brutal. Oak-free, galaxy is one spiral among countless spirals. It is one member of a small group. That group rides a filament. The filament is part of a web. The web is mostly void. The web's nodes build monsters. The web's outskirts hide ghosts. The web is expanding, and the expansion has horizons that will eventually erase much of the web from view. That is the terrifying part. Not that we are insignificant, but that we are temporary observers in a universe whose accessibility is time-limited, and that's why the terror is so clean by the end. The universe isn't threatening you with monsters because it wants to scare you. It's showing you the consequences of gravity operating for a very long time in very different neighborhoods. In some places, gravity builds ghosts, quiet, hard-to-see reservoirs of mass. In others, it builds kings, centers that grow by consuming the traffic the web delivers. Our galaxy sits between those extremes, and that between is not comforting. It's temporary. And here is the final twist that keeps the terror from turning into emptiness. The deepest, strangest anomaly in this entire story is not an impossible galaxy. It is not a ghost galaxy. It is not a cluster monarch with a halo fading into intracluster light. It is the fact that, in one mid-sized spiral on the edge of a modest group, the universe assembled matter into a species that can build a mirror, cool it to tens of kelvins, point it into darkness, and read the earliest light like a confession. Webb didn't make the Milky Way small. It made the Milky Way accurately placed. It revealed the crowd. It revealed the extremes the web can produce. It revealed that our galaxy's shape is a local phase, not a cosmic entitlement. And it revealed something even more unsettling: that our moment in cosmic history is unusually good for seeing the universe's structure. We live in an era when the web is still on display, when the sky is still full of distant lights, when the universe's own past can still reach us. The Milky Way is tiny. The universe is enormous. The web is ruthless, and yet, for a brief window, the cosmos is readable, and we are the part of it doing the reading. That, more than any deep field, is the terrifying revelation hiding behind all the beauty. The universe is not only vast enough to make you feel small, it is vast enough to make your awareness feel like the rarest thing it has ever produced. And until we find another place where something looks back, that rarity sits right here, inside this tiny spiral, staring out into the dark and realizing the dark was never empty at all.